Okay, so now let's have a look at an example. We're going to try and prove something using vector addition and scalar multiplication. So I'm going to prove that the two diagonals of a parallelogram bisect each other. So here I've drawn my parallelogram, and I've drawn the two diagonals in red and blue. So I'm trying to prove that this red line and the blue line cut each other in half. That this point is exactly halfway along the red one and halfway along the blue one. So we'll start off by formulating this problem in terms of vectors. I'm going to call the line that goes up the left-hand side the vector A. And then I know that the one that goes up the right-hand side is also A because it's parallel and it's got the same length. And I'll call the one across the bottom B. Then I know the one across the top is also B because it's parallel and has the same length. And then I'll call this red diagonal C and the blue diagonal D. Okay, so when we approach a problem like this, it's something perhaps a little bit unfamiliar. We don't necessarily know exactly how the entire proof's going to work out at the beginning, but we don't have to feel worried about that. We're just going to start off by writing down what we do know, and then we just kind of follow our nose through. So at each stage we just say, okay, what can I do next? What can I do next? What can I do next? And we hope that we get somewhere in the end. So here I'm going to start off by expressing C and D in terms of the vectors A and B. So we can see that going along C is the same as going along A and then along B. So the vector C is equal to A plus B. And similarly, going along D is the same as going backwards along B and then along A. So D is equal to minus B plus A, or in other words, A minus B. Okay, and I want to think about this point of intersection here. So I'm going to consider this vector, which I'll call X. Because X lies on the intersection of the red line and the blue line, I can express X in two different ways. So first of all, I know that X points in the same direction as C, so I know that X is some multiple of C. I'm trying to show that actually it's a half of C, but I don't know that yet. What I can say at the moment is that X is equal to lambda times C for some scalar lambda. But going along X, we can see, is the same as going along B and then going part way along D. So I can also say that X is equal to B plus mu times D for some scalar mu. And then I'm trying to prove that actually I have to go halfway along C and I have to go halfway along D. So I'm trying to prove here that lambda and mu are both a half. So my aim now is to show that lambda and mu are both a half. Okay, so let's set off and see what we can do. I'm going to start by identifying these two expressions for X. So that tells me that lambda times C is equal to B plus mu times D. And now I'll substitute in the expressions I've got for C and D. So that will give me that lambda times A plus B is equal to B plus mu times A minus B. Okay, we know that we can multiply out brackets when they appear like this, so let's do that. That gives us that lambda A plus lambda B is equal to B plus mu A minus mu B. And now I think I'll rearrange my terms so that I've got all the terms involving A on the left-hand side and all the terms involving b on the right hand side. So that's going to give me that lambda a minus mu a is equal to b minus mu b minus lambda b. And then I'll tidy up a little bit, so I'm going to factorise again, and I've got lambda minus mu times a is equal to 1 minus mu minus lambda times b. Okay, so all I've done so far is I've written down two different expressions for the vector x, I've equated them, and then I've just rearranged things a little bit until I've got to something that looks quite useful. So let's have a look at this expression we've got now. What does this say? It says that some multiple of a is equal to some multiple of b. But if we look at the picture, we can see that a and b point in different directions. So the only way we can possibly have a multiple of a equal to a multiple of b is if actually I've got 0 times a and 0 times b. So that tells me that I must have lambda minus mu equals 0 and 1 minus mu minus lambda equals 0. Another way to see that is to say, well, what if lambda minus mu was non-zero? Well, if it's a non-zero number, then I can divide by it. So I can divide this vector equation by lambda minus mu, and I'd end up with an expression for a as a multiple of b. But we can see that that can't possibly happen because here's a and here's b pointing in a totally different direction. Okay, so remember we're trying to show that lambda and mu are both a half, and so far I've obtained these two equations involving lambda and mu. So all I need to do now is solve these equations. So the first one tells me that lambda must be equal to mu, and then substituting that into the second one, I've got that 1 minus 2 mu is equal to 0. And solving this one, I obtain that mu is a half. So finally, I've proved what I aim to prove, that lambda and mu are both a half. So looking back here, we can now conclude that the vector x is exactly a half times c, or equivalently, it's b plus exactly a half times d. So finally, we have proved that these two diagonals do bisect each other. Okay, so I think this is quite a nice problem because we've had to use our knowledge about vectors and a bit of our intuition to work through something slightly unfamiliar. And these are skills that we really try to develop in university maths. We don't just want our students to know things and to be able to do things. We really want them to develop a deep understanding of what they're doing and to build their mathematical intuition so that they can approach and try to think through slightly more unfamiliar problems. Okay, I'd just like to finish by saying a few words about how we can generalize these notions to higher dimensions. So far we've talked about two-dimensional vectors, say vectors u with components u1 and u2, and we've talked about three-dimensional vectors, say vectors v with three components v1, v2 and v3. But there's no reason why we should stop there. We can very easily just define an n-dimensional vector to be a vector, say, w, that has n components. So w1, w2, and so on, all the way down to wn. So speaking purely algebraically, the definition of vector in this way generalizes very easily from the two- and three-dimensional case to the n-dimensional case. And we can also generalize the notions of vector addition and scalar multiplication. So for example, if I have another vector, say y, with components y1, y2, and so on, down to yn, then we'll just define w plus y to be the vector w1 plus y1, w2 plus y2, and so on, all the way down to wn plus yn. And similarly, if I have a scalar lambda, so just some number lambda, then lambda times w will define to be lambda w1, lambda w2, and so on, all the way down to lambda wn. So still looking just algebraically, the component-wise definition of vector addition and of scalar multiplication generalise in a very natural way from the 2- and 3-dimensional case to the n-dimensional case. But what about if we want to think about some geometric intuition? Well, remember, we think of 2-dimensional vectors as sitting in 2-dimensional space. That is the space with 2 coordinates that we usually call x and y. And we think of 3-dimensional vectors as sitting in 3-dimensional space. That is the space with 3 coordinates that we usually call x, y, and z. And in an entirely analogous way, we should think of n-dimensional vectors as sitting inside n-dimensional space. And we can think of that as just the space with n coordinates that we often call x1, x2, and so on, up to xn. And what about our geometric interpretation of vector addition and scalar multiplication? Well, we know that in the 2- or 3-dimensional case, multiplying by a scalar lambda has the effect of scaling our vector by a factor of lambda. And you should also bring that intuition to the n-dimensional case. So we should think in the n-dimensional case of multiplying by lambda as having the effect of somehow scaling our vector lambda. And similarly, where in the 2- and 3-dimensional case, we think of vector addition as this kind of top-to-tail composition of directed line segments, you should also bring that intuition to the n-dimensional case and think of vector addition in the n-dimensional case as some kind of top-to-tail addition of vectors. So as well as these operations, many other concepts that you might know from 2- and 3-dimensional vectors also generalise to the n-dimensional case. So for example, we can talk about the length of an n-dimensional vector. And just as in 2 or 3 dimensions we have a dot product, we can also define a dot product in the n-dimensional case. And we can start thinking about certain shapes inside n-dimensional space. So where we might talk about the vector equation of a line or a plane in 2- and 3-dimensional space, similarly you can talk about the vector equation of a line or a plane in n-dimensional space. So I just wanted to give a little bit of an idea of how we can start thinking about vectors in higher dimensions. And you can see that we can define everything in a purely algebraic way, and then we bring geometric intuition from the 2- and 3-dimensional case. So in this way you can see that it's not necessarily as hard as you think to start thinking about higher dimensional spaces.